For this next part of Notes 15, we're going to focus on how programs like SAS, but also other programs that you might encounter after this class, summarize the results of the ANOVA test, and it's usually done in something that we call an ANOVA table that you can see here below. So the way this table is set up is we are looking at the variability between groups and the variability within groups, just like we've been doing on the previous pages. And for each of those, we're going to look at a couple different things. We're going to look at the degrees of freedom associated with each, so the numerator degrees of freedom and the denominator degrees of freedom. We're going to look at what we call the sum of squares for both, so sum of squares between and sum of squares within. We're going to look at the mean squares between and the mean squares within, and then we're going to include our test statistic and our p-value. And so all of that information is going to be put together in a nice concise table that other people can use. All right, so just a quick recap. SSB is sum of squares between groups. We haven't actually talked about this very explicitly, but this is just the numerator from mean squares between that we spent a page looking at earlier. Sum of squares within groups, SSW, is the numerator from mean squares within before. Again, something we spent a page looking at. And then really, one of the only new calculations in this table is what we call sum of squares total, but this is just adding SSB and SSW here. You'll notice that for the degrees of freedom, we also add those together to get a total in that column as well. And then you'll notice MSB, that's just SSB divided by I minus 1. MSW is just SSW divided by N minus I. And so for both of these, oops, this number here is just this number divided by this number. This one is this number divided by this number. And if we recall our test statistic is just this divided by this. So we've got all of the pieces here. I want to remind you that be careful when you're doing these calculations. I's and 1's tend to look very similar. So remember that the degrees of freedom for the numerator is I minus 1. And for the denominator is n minus I, not n minus 1. All right, so what does this look like for the serial example that we've been working on? You might want to go through and try to find where we calculated each of these numbers before, but basically everything in the between and the within row are things that we previously calculated. So mean squares with between we calculated, and that was just this divided by this if you look back at the formula. Mean squares within we calculated, that was just this divided by this. And in our last video, we looked at the test statistic and the p-value. And so these two calculations are new, but they're just adding the two things above them to get totals. So if we wanted to do this in SAS, we will use the GLM procedure, and it's going to look hopefully fairly similar to several other things we've done in SAS. We're going to put proc GLM data equals, and we would need to put the name of our data set. We would put class and whatever our qualitative variable that's splitting our data into groups is. And then we're going to have a line that says model. We're going to put the quantitative variable that we're studying, an equals sign, and the qualitative variable that we're studying. So we can go to SAS Studio right now and look at this for our serial example. So in SAS On Demand, I've opened the 15-serial file. And just as a reminder, what I usually do is I'll open a new program because otherwise you might get some messages popping up that are telling you you're not supposed to be editing the file that you're working with. And I'm going to do proc GLM data equals. My data set is called stores, so I'll put that in. We said we need a line that says class and tells us which variable is splitting our data into groups that we're comparing. In this case, we're comparing the different packages, so I would put class package. And on the model line, we said that we're going to put our quantitative variable, an equals sign, and our qualitative variable. So in this case, serial equals package. And we'll see something similar to this actually in another set of notes coming up. And we'll revisit this idea of why we write it out this way when we get there. But for now, I'm just going to highlight the data and the proc GLM code that I just typed, I'm going to click on the little running person here, and it'll take a second, but hopefully what we see will look a lot like what we just saw in the notes here. So this line here that says model is what we called between in the notes. Error is what we called within. And you'll notice that a lot of these numbers look very similar to what we just wrote out in the notes. All right, so we can use this to double check that all of our calculations were good. And this is how we'll do most of these problems in the future, is we're not going to do these calculations by hand, but like other problems that we've worked through earlier this semester, it's helpful to know where these numbers are coming from. It's tempting to want to just jump right in and run something in SAS, but if you do that and you don't quite know, what these numbers mean, it's a lot harder to properly understand the results, and you're much more likely to make mistakes. So that's really our goal here, is to make sure that before you jump in and let the computer take over the calculations, you have an understanding of what's happening in those calculations and why it's providing us with the answers that we're seeing here. And one other thing that the GLM procedure will give us is box plots comparing our different groups. And one thing that I want to point out is that, remember, our null model said all of the population means are the same. And so if you look at box plots for your data, one thing that you might want to look for is, are there cases where you would feel pretty convinced looking at this picture that certain groups would have different population means? So for example, if I look at groups 1 and 2 here, the diamonds are the sample means, and those things are fairly close together. They're not exact. But another thing I might notice is that there's a lot of overlap between the sales for package design 1 and package design 2. So maybe I'm not that sure which one of these is better or if they're even different. On the other hand, when I compare something like package design 4 to both of these, there's almost no overlap. Every store that used package design 4 sold more than every store that used either 1 or 2. And so these are the types of things that would probably convince me that, yeah, there really is something going on here. This seems like it probably wouldn't happen by chance alone. And so there'll be an activity where you'll get a chance to try this out a little bit as well. But this is something that I wanted to point out, that a lot of times it's helpful to have a visual in addition to that p-value and that conclusion that you wrote. So I'm going to go back to the notes here, and we got the same results in our table. SAS only writes less than 0.0001 for the p-value instead of going out to 6 decimal places like we did, but everything else should look the same. So that's basically the ANOVA test. We will, in upcoming notes, look at what we would do about confidence intervals if we wanted to see not just is there a difference between the population means, but which groups are different, how different are they? And then I mentioned previously that we've skipped over assumptions, and so we'll come back to talk about those as well. One last thing you can do with the notes here is there's an example B where you have a ANOVA table that has some blanks in it, and the question asks you to try to fill in the parts that are blank using the relationships in the table that we talked about a page or two ago. If you haven't done this yet, I recommend pause the video, try it on your own, see if you can figure out how all of these things relate. I'm giving you a few more seconds to do that, and then I'll walk through how I filled in the answers here. But try it on your own. So here is the completed table. The ones that are in black are what was given to you. The ones that are in red are things that I filled in. So one thing that I could remind myself of is that these two numbers get added together to give me my total degrees of freedom. So if I had 24 here, I know that this needs to be 7 so that these two things add up to 31. Then I would move over to the sum of squares, and I would realize that I can do something similar here. These two things added together need to be 70,907, and so I would just take this minus this to figure out that the sum of squares between must be 35,819. Then we keep moving over on the table, and we said that the mean squares between is just the sum of squares between divided by the degrees of freedom between. So I would take this number divided by this number to get my 5,117. And I would do something similar for the mean squares within. I would take 35,088 divided by 24, and I would get this number here. I'm almost all the way through the table now. To get my test statistic, it's the mean squares between divided by the mean squares within. So I'm taking 5,117 divided by 1,462. That gets me 3.5. And then the last step to get my p-value is I would go and use StatKey. And I would say, okay, I've got an F distribution with 7 for the numerator degrees of freedom, 24 for the denominator degrees of freedom, and I'm shading everything above 3.5. So let me go over here now. I'm going to change this to 7 and 24. I'm going to click right tail. I'm going to shade above 3.5, and there's that 0.0099. All right, so that's how I would fill in the table. There's a couple other questions that are asked here. How many groups were in the study? The numerator degrees of freedom is our number of groups minus 1. If that's 7, then my number of groups must be 8, so that when I do 8 minus 1, I get 7. Here's the picture I just showed you in StatKey with the p-value. And if I was doing an actual ANOVA test based on this, because my p-value is less than 0.05, I would take this to be sufficient evidence that at least one of the population means from those 8 groups is different from another. So if you feel like this might be something that's a little bit hard to do, there's a link here that you can click on that will give you ANOVA tables with certain parts missing, and you can get some practice trying to solve those by filling in the blanks, just like we did at the top of this page.